This is the fifth video in a series where I cover everything you need to know to build a GPS receiver from scratch. In the previous video, we learned how to sample signals from GPS satellites so we can access them in code. However, while there are around 30 satellites in the GPS constellation, only a few of them will be in the sky above a receiver at any given time. The receiver needs to determine which satellites it can hear and the parameters that result in the strongest signals. These are the goals of the acquisition stage, which we'll be covering in this video. More specifically, we'll talk about the parameters that affect the strength of the satellite signals, how to find the best values of those parameters, the size of the space we need to search for them, and how we use them to determine if the satellite is present. Let's start with the parameters. If we want to acquire the signal of a particular satellite, there are two parameters that determine the signal strength. The first of these is the phase of the satellite's PRN code. Remember from the GPS signals video that to decode a satellite's navigation message bit, we calculate the correlation of 1 millisecond of received signal with a copy of the satellite's PRN code. If the copy is aligned with the PRN code within the signal, we get the navigation message bit. If they're not aligned, we just get noise. In order to align them, we need to know the phase of the PRN code within the signal. That's this parameter. The second parameter is the frequency shift of the satellite's carrier wave. You might be saying, hang on, I thought all satellites transmitted their CA signals on the L1 frequency. What's this about a frequency shift? Well, they do, but satellite signals can be Doppler shifted. Let's look at a visualization to demonstrate why. Here we have a satellite orbiting Earth, on which is a receiver. The red arrow is the satellite's velocity, and the green arrow is the component of that velocity in the direction of the receiver. At the moment, from the receiver's perspective, the satellite is rising above the horizon. A large component of the satellite's velocity is directed towards the receiver. In other words, it's moving towards the receiver. This means that due to the Doppler effect, the receiver will observe a slightly higher frequency than the L1 frequency. As the satellite continues rising, it moves towards the receiver at a slower rate, so the observed frequency decreases. When the satellite is directly overhead, it's not moving towards or away from the receiver, so the observed frequency is equal to the L1 frequency. After the satellite has passed overhead, it's moving away from the receiver, so the observed frequency continues decreasing until the satellite sets over the opposite horizon. Okay, so the signal's frequency can be shifted. How does that affect its strength? Well, let's step through 4 examples to demonstrate. In each example, we'll sample the satellite signal for 1 millisecond and calculate its correlation with the satellite's PRN code to determine the signal strength. For the first example, imagine we had direct access to the satellite's modulation signal, that is, the product of its navigation message and PRN code. If we use a constellation diagram to visualize the samples we get from this signal, you can see that they're located at plus and minus 1, as we expect. Let's add a third dimension, time, to this graph so we can see how the samples change over time. Again, you can see that some of the samples are at plus 1 and some are at minus 1. Next, let's calculate the correlation of these samples with a misaligned copy of the satellite's PRN code. On the left, we have the samples over time, and on the right, we have the PRN code over time. If we multiply each sample by the corresponding PRN code value, we get the following. You can see that there's still a mix of positive and negative values. If we sum these, they mostly cancel, and we're left with a correlation of -2. The magnitude of this correlation, its distance from the origin, is a measure of the signal strength, and in this case, it's weak. For the second example, let's consider what happens if we use the same modulation signal, but the PRN codes are aligned. Again, on the left we have the samples over time, and on the right we have the PRN code over time. Now when we multiply them, the PRN code within the signal and the copy of the PRN code are equal, so their product is always 1, leaving only the navigation message bit. When we sum these values, they add constructively, and we're left with a correlation of 2046, much larger than before and a stronger signal. This is yet another way to show why it's important for the PRN codes to be aligned. For the third example, let's consider a modulated signal that isn't frequency shifted. That is, it's the product of the navigation message, the PRN code, and the carrier wave. As we discussed in the sampling video, when we perform bandpass sampling, the carrier wave is replaced with a complex constant, AE to the J phi, where A is the amplitude of the carrier wave and phi is its phase. That means the samples will be equal to plus or minus AE to the J phi, which is plus or minus 1, scaled by a factor of A, and rotated through an angle phi. Let's visualize this on a constellation diagram. We have the points at plus and minus 1 as before, but this time we can scale them by changing the amplitude of the carrier wave, and rotate them by changing its phase. Introducing time as a third dimension again, we can see how these parameters affect the samples over time. Multiplying the samples by an aligned PRN code leaves the navigation message bit as before. However, this time, it may be scaled or rotated. Summing these values, they still add constructively and indicate a strong signal, but the resulting correlation may too be scaled or rotated. It's useful to know this rotation when we're trying to decode navigation message bits, but for the purposes of the acquisition stage, we're only interested in the signal strength, and we can ignore the rotation for now. For the fourth and final example, let's consider a modulated signal that is frequency shifted. I've replaced the term f of t with g of t to indicate this different frequency shifted carrier wave. As we discussed in the sampling video, a frequency shifted signal is the same as a signal with a constantly changing phase. Bandpass sampling will still replace the carrier wave with a complex constant, but the angle of that constant will change with every sample. That means samples will be equal to plus or minus 1, scaled by a factor of A, rotated through an angle phi, and further rotated through an angle 2 pi delta ft, where delta f is the frequency shift and t is the time at which the sample was taken. This final angle will be different for each sample because t is different for each sample. If we visualize this, we can still scale the samples using A and rotate them using phi. But when we apply a frequency shift, the constant rotation causes them to twist into a helix. So what happens when we calculate the correlation this time? Well, multiplying by an aligned PRN code leaves the scaled and rotated navigation message bit as before. However, the constant rotation resulting from the frequency shift prevents them from adding constructively and affects the magnitude of the correlation. You can see that as I increase the frequency shift, the correlation gets closer and closer to the origin, a weaker and weaker signal. So how can we recover the strong signal that we know is in there? Well, we know our sampling rate, so we know the time at which each sample was taken. If we also know the frequency shift, delta f, we can undo each sample's rotation by multiplying it by e to the negative j 2 pi delta ft. After doing that, we can calculate the correlation as before and see the strong signal. This process is called carrier wipe-off, and it's why we need to know the frequency shift of the carrier wave. Hopefully that explains why we need to know the PRN code phase and the carrier wave frequency shift. The next question is, how do we find them? And the answer is brute force. There's a range of possible PRN code phases and a range of possible carrier wave frequency shifts. We simply test each combination to find the one that results in the strongest signal. You can imagine it as a three-dimensional graph, with phase on the x-axis, frequency shift on the y, and signal strength on the z. If we test all the combinations, we get a graph like this, where it's easy to spot the combination that results in the strongest signal. The process of calculating the strength of a particular combination is a little different from the examples we just talked through. We want to calculate the correlation over a longer period of time to strengthen the signals, say 10 milliseconds. However, this increases the chance that the navigation message bit will change during that period. If that happens, some of the samples will cancel each other out, resulting in a smaller correlation. To avoid this, we calculate the correlation over multiple 1 millisecond periods and add their magnitudes. This strengthens the signal as it does with one long period without the risk of samples cancelling each other out. This is called non-coherent integration. I said there's a range of phases and a range of frequency shifts. But what are those ranges? How many combinations do we have to check? Well, our sampling rate is 2.046 MHz, meaning we take 2046 samples per millisecond. The PRN code is 1023 bits long and repeats once per millisecond. That means there are 2 samples for every bit. It's a little easier to calculate correlations if it's a one-to-one correspondence, so we upsample the PRN code. That is, we repeat each bit twice to make it 2046 half bits long. That means there are 2046 phases to check. And what about frequency shifts? Well, what's the maximum frequency shift we could expect to see? A satellite moves towards or away from a receiver at the greatest rate when it's rising or setting over the horizon. A little trigonometry shows that at this point, it moves relative to the receiver at around 0.93 kilometers per second. Plugging this into the Doppler shift equation, we find that would result in a shift of plus or minus 4.9 kHz. The rotation of the Earth could result in another plus or minus 2.4 kHz, and motion of the receiver, for example if it was in a car, could result in another plus or minus 150 Hz. That gives a total of around plus or minus 7.5 kHz, and means we need to search all of the shifts between negative 7.5 kHz and positive 7.5 kHz. That's a lot of computation just for 2 parameters, but we have to do it. There are techniques we can use to avoid having to test every single combination, like gradually narrowing down on promising areas and using the fast Fourier transform, but I won't go into those here. If you'd like to learn more, check out the Acquirer class in my GPS receiver implementation on GitHub. I've left a link in the description. So that's how you determine the best parameters for a particular satellite. But how do we use them to check if the satellite is present? Well, on startup, the receiver finds the best parameters and the associated signal strength for every satellite in the constellation. The satellite signal strength is compared against a threshold that's determined experimentally. If the strength is greater than the threshold, the satellite is considered present, and its parameters are passed to the next stage, the tracking stage. On the other hand, if the strength is below the threshold, the satellite is considered absent. Remember though, satellites constantly move through the sky, so even if one's not present now, it might be soon. For that reason, we periodically try to acquire satellites that we're not actively tracking. Let's recap the important points from this video. First, in order to acquire a strong satellite signal from which we can decode navigation message bits, we need to determine 2 parameters. The first is the phase of the PRN code within the signal. This is used to align the copy of the PRN code when calculating correlations. The second is the frequency shift of the carrier wave. This is used to undo the effects of that frequency shift, the constant rotation of samples, which is also known as carrier wipe-off. Second, the best values for these parameters are found through a brute force search of the parameter space. The combination that results in the strongest signal is the best. Third, it's quite a large parameter space. On one axis we have 2046 possible PRN code phases, and on the other we have frequency shifts in the range plus or minus 7.5 kHz. And finally, in order to determine if a satellite is present, we calculate the best parameters and their associated signal strength, and compare that signal strength against a threshold. If it's above the threshold, the satellite is present. If it's below the threshold, it's absent, and we should check again later. In the next video, we'll cover the third stage of the GPS receiver implementation, tracking. We'll learn how to track signal parameters over time so we can continue to decode navigation message bits as satellites move across the sky.